Right now, on the other side of the Pacific Ocean, the seafloor off the coast of Russia is shaking in a pattern that almost exactly mirrors what California started doing 24 hours ago. 8 earthquakes above magnitude 4.5 in roughly 36 hours, all inside a 50-kilometer box, all on a segment the Japan Meteorological Agency has been officially watching since last year's magnitude 8.8 event left it loaded. The most recent earthquake came in just hours ago. The cluster is not slowing down, and on the other corner of the same plate that covers 20% of the surface of this planet, the southern Cascadia margin is also still adding events on the same 48-hour clock. 2 simultaneous clusters, 2 opposite locked corners of the largest plate on Earth, both still developing, both on segments already officially flagged. What that means, and what every seismologist watching this pattern tonight is quietly trying to figure out, is exactly what this video is about. One thing before we get into it: if you find what we do here useful, hit like and subscribe so you do not miss the follow-up when the catalogue updates, and let me know in the comments where you're watching from, because the answer to the question this video is asking matters differently, depending on which coast you are on. Now, here is the honest version of what we know tonight. There is a question sitting inside this pattern that the literature cannot cleanly resolve: whether 2 clusters firing on opposite corners of the same plate in the same 48 hours mean something, or whether they are the most ordinary thing in the world, the catalogue accidentally lining up because the catalogue occasionally lines up. The honest answer is that the simultaneity is statistically unusual, but not unprecedented, that each cluster has its own local mechanism that fully explains why it is happening where it is happening, and that the question of whether the simultaneous visibility means more than each cluster considered alone is exactly the kind of question the formal stress transfer literature treats with a great deal of caution. We're going to walk through what that literature says. We're going to walk through what the energy arithmetic forecloses. We're going to walk through the 3 readings of this pattern that the seismological community would consider defensible, and we're going to land at the end on what every person watching the catalogue tonight is actually asking themselves, whether they are saying it out loud or not. Before any of that, there is one thing to hold in your mind as a foundation. The Pacific Plate moves at approximately 7 to 10 centimeters per year in a roughly west-northwest direction across the surface of the Earth. It has been moving that way for tens of millions of years. Its area is approximately 103 million square kilometers, roughly 20% of the planet's entire surface. It is a single rigid body. Its 2 locked corners, the one off the coast of California and Oregon and the one off the coast of Russia, are connected through that body. They are part of the same machine. What you are about to see is what happens when both ends of that machine produce visible catalogue activity in the same 48 hours. Whether that visibility is meaningful, or whether it is a kind of optical illusion produced by 2 independent clocks happening to fire at the same time, is the question the rest of this video investigates. The place to start is the cluster that almost no one in the West is reporting yet. The cluster sits in a small patch of the Pacific Ocean, centered roughly on 51 degrees north latitude and 159.5 degrees east longitude. To make that location concrete, hold a globe in your mind. Find Japan. Move your finger north along the chain of Russian islands that arcs from the northern tip of Honshu up toward the long thin peninsula that hangs south from the eastern Siberian coast. That peninsula is Kamchatka. The cluster sits in the ocean directly off the southeastern coast of the peninsula, about 150 to 200 kilometers south-southeast of the city of Vilyushinsk, which sits on Avacha Bay near the southern tip of the peninsula. Vilyushinsk is the home base of the Russian Pacific Fleet submarine forces. Petropavlovsk-Kamchatsky, the regional capital, sits a few kilometers north of Vilyushinsk on the same bay. Together, those 2 cities hold the bulk of the peninsula's 300,000 or so residents. The cluster spans approximately 50 kilometers from north to south, and a tighter distance from east to west. Inside that small box, here is what the international seismic catalogues have logged across the last roughly 36 hours. We will go from the most recent event backward through the sequence. The most recent event at 17 hours and 13 minutes. Universal time on June 4th, 2026, was a magnitude 5.1 reported by the GFZ German Research Center for Geosciences in Potsdam, the Central German Seismological Authority. Epicenter, 51.88 degrees north latitude, 159.18 degrees east longitude. Depth, 10 kilometers. That depth places the event right at the shallowest end of the megathrust interface zone, the depth band where the locked patch between the Pacific Plate and the Okhotsk microplate sits. A 10-kilometer depth event in this geometry is the canonical interface earthquake signature. It is not a quirky deep slab event. It is not a peculiar near-surface oceanic crust event. It is a textbook megathrust interface earthquake at the shallow end of the interface depth range. Working backward from there, earlier on June 4th, at 2 hours and 32 minutes Universal Time, the Russian Academy of Sciences Geophysical Service, abbreviated GSRAS, logged a magnitude 4.6 at 51.42 degrees north and 159.64 degrees east at 20 kilometers depth. 2 hours later, at 4 hours and 34 minutes Universal Time, the same agency logged a magnitude 4.5 at 51.72 degrees north and 159.62 degrees east at 45 kilometers depth. That second event is immediately notable because the depth is much deeper. 45 kilometers is well into the upper portion of the subducting Pacific slab itself, below the megathrust interface, into the slab mantle that has already descended past the locking zone. Step backward through the night before, June 3rd, and you find the largest event in the cluster so far. At 17 hours and 23 minutes, Universal Time on June 3rd, the European Mediterranean Seismological Center logged a magnitude 5.2 at 51.634 degrees north and 159.403 degrees east at 20 kilometers depth. The same event appears in the United States Geological Survey Catalog under event identifier US 7000SQCW, listed as 188 kilometers south-southeast of Vilyushinsk, with depth recorded at 10 kilometers on the USGS side. The small variation between the two authorities, 20 kilometers from the EMSC, 10 kilometers from the USGS, reflects normal cross-catalogue variability. Both agencies are reporting the same physical event from different seismic station networks and different waveform inversion processes. The variation sits well within the typical error envelope for events at this distance and depth range. Roughly 45 minutes after that magnitude 5.2, at 18 hours and 9 minutes Universal Time on June 3rd, the European Mediterranean Seismological Center logged a magnitude 4.7 at 51.574 degrees north and 159.508 degrees east at 20 kilometers depth. The USGS catalogues a corresponding event as 181 kilometers south-southeast of Vilyushinsk at 25.7 kilometers depth, under event identifier US 7000SQDB. The Russian Academy of Sciences Geophysical Service adds 2 more events on June 3rd. A magnitude 4.6 at 17 hours and 32 minutes Universal Time at 51.2 degrees north and 159.84 degrees east at 40 kilometers depth, and a magnitude 4.6 at 20 hours and 15 minutes Universal Time at 51.49 degrees north and 159.99 degrees east, also at 40 kilometers depth. The European Mediterranean Seismological Center contributes a magnitude 4.5 at 20 hours and 3 minutes, Universal Time on June 3rd, at 51.5318 degrees north and 159.6651 degrees east, at 32 kilometers depth. The USGS catalogues an additional magnitude 4.5 under identifier US 7000SQEC, listed as 179 kilometers south-southeast of Vilyushinsk at 35 kilometers depth. Add those up, accounting for the small differences between catalogues that are just different agencies reporting the same underlying events from different stations, and you get a cluster of approximately 8 to 9 confirmed magnitude 4.5 and above earthquakes in roughly 36 hours inside a box less than 50 kilometers across. That is not the activity rate of a normally behaving piece of seafloor. That is the activity rate of a fault system that is doing something. The largest event in the sequence, the magnitude 5.2 at 17 hours and 23 minutes Universal Time on June 3rd, is the reference point around which everything else is measured. The most recent event, the magnitude 5.1 at 17 hours and 13 minutes Universal Time on June 4th, arrived almost exactly 24 hours later. In magnitude terms, it is only fractionally smaller than the largest event. The cluster has been running for 36 hours. It is still adding events, and the agencies logging those events represent 4 independent national and international monitoring authorities: the GFZ in Potsdam, the EMSC in Bruyères-le-Châtel, the USGS in Golden, Colorado, and the Russian Academy of Sciences Geophysical Service in Moscow, all recording the same physical reality from different corners of the global seismic network, and all arriving at the same conclusion. The cluster is real, the cluster is dense, the cluster is current, the event log is the raw material, the depth distribution is where the cluster starts to say something that goes beyond a simple count of events. The shallowest event in the sequence, the most recent magnitude 5.1, sits at 10 kilometers. Several of the mid-cluster events sit at 20 to 25 kilometers. One sits at 32 kilometers. One sits at 35 kilometers. The deepest event in the catalogue sits at 45 kilometers. That range, 10 kilometers to 45 kilometers, spans almost the entire vertical extent of the megathrust interface and the upper portion of the subducting Pacific slab at this longitude. To understand why that matters, it helps to know what sits at each of those depths. Above 10 kilometers is mostly oceanic sediment and uppermost oceanic crust, the material that has not yet been drawn down into the subduction zone and is too weak and too poorly consolidated to store the kind of elastic strain that produces magnitude 4.5 and above earthquakes on a megathrust interface. Below 45 kilometers, at this latitude and longitude, is mostly slab mantle, the deepest part of the subducting Pacific slab that has already descended well past the zone of maximum locking. Between 10 and 45 kilometers is the megathrust interface itself, the locked patch where the Pacific plate is pressed against the Okhotsk microplate. Friction is preventing the two from slipping, and elastic strain is accumulating at a rate set by the convergence velocity of the two plates. That is the zone where the largest earthquakes on this arc are generated. That is the zone the entire cluster has lit up. A single rupture, a small earthquake at one fault patch, followed by a sequence of aftershocks decaying around it, would typically produce events within a much narrower depth range. The primary patch fires, stress redistributes locally onto nearby patches at similar depths. The aftershock cloud tightens around the main rupture surface. The depth spread of the cloud is usually a few kilometers, occasionally 10, rarely more. What the Kamchatka cluster is showing is different. Events at 10 kilometers, events at 20 kilometers, events at 32 kilometers, events at 45 kilometers, all within the same 50-kilometer horizontal footprint, all within 36 hours. That depth spread, 35 kilometers of vertical range across the full mechanical extent of the interface, is more consistent with a broader regional stress increment, activating multiple discrete fault patches across the full interface than with a single patch firing and its local stress field decaying around it. The temporal pattern reinforces that reading. The cluster did not produce all its events in the first 6 hours and then taper. It produced events on the evening of June 3rd Universal Time, through the night of June 3rd into June 4th Universal Time, and again on the afternoon of June 4th Universal Time. 3 or 4 distinct visible pulses across the 36-hour window, each separated from the next by enough quiet time that they are not the immediate aftershocks of a single main shock decaying under Omori's law. Omori's law, originally formulated by Fusakichi Omori in 1894 and refined by Tokujitsu in 1961, states that the rate of aftershocks following a main shock decays roughly as the inverse of the time since the main shock. If a cluster produced 10 aftershocks in its first hour, the law predicts approximately 5 in the second hour, 3 in the third, 2 in the fourth, and so on, a smooth inverse time decay that drops the rate steadily towards zero. The Omori prediction for this cluster, if it were a single main shock plus aftershock sequence, would have the event rate dropping steadily across the 36-hour window. That is not what is happening. The cluster is sustaining its event rate. It is not tapering. Sit with that for a moment. The cluster has been active for 36 hours. The largest event occurred at the 17-hour mark of that window. Under Omori decay, the cluster should by now be producing events at roughly 1/40th the rate it produced in the first hour after the largest event. Instead, it produced a magnitude 5.1, only fractionally smaller than the magnitude 5.2 that stands as the sequence's largest event, almost exactly 24 hours after that largest event. That is not a decaying sequence. That is a sequence that is sustaining. These three observations, the dense 50-kilometer spatial footprint, the full-depth interface activation from 10 to 45 kilometers, and the sustained event rate with no Omori decay, are the technical signatures of a fault system under sustained or recently elevated stress. Not a fault system that fired once and is decaying toward background. Not a routine swarm of microseismicity on a creeping segment. A fault system that is doing something, and that has been doing it continuously for 36 hours as of this recording. Whether the source of that sustained stress is entirely local to this segment, the natural ongoing settling of Coulomb stress redistribution from something that happened nearby in the recent past, or whether it reflects something larger that connects to what is happening on the other side of the Pacific Ocean at the same moment, is the question the rest of this story investigates. To pursue it honestly, the first thing needed is context. Context about where this segment sits in the larger architecture of the Pacific Rim, why a cluster here carries different weight than a cluster on a less loaded piece of seafloor, and what the same trench has done in the past when clusters like this one turned out to be the prelude to something much larger. That context begins with geography, with placing Kamchatka on the map in a way that makes the tectonic stakes of what is happening there tonight legible to a viewer sitting anywhere on the other side of the ocean. For most viewers, Kamchatka is one of those places on a map that exists in a kind of geographic blur. It is far away. It is Russian. It is in the part of the world where Russia meets Alaska across the Bering Sea. It is the place where some of the largest brown bears on the planet live, where there are more active volcanoes per square kilometre than almost anywhere else on Earth, where the cities on the southern coast face out across an ocean that takes a very long time to cross to reach anywhere familiar. That blur is understandable for most purposes. It is not acceptable tonight, because the precise position of Kamchatka on the geological map of the world is exactly the thing that makes this cluster worth the attention it is about to receive. The Kamchatka Peninsula juts south from the eastern Siberian coast into the northwestern Pacific Ocean. In geographic area, it is roughly the size of California, approximately 470,000 square kilometers, but it holds only about 300,000 people, most of them concentrated in the south near Petropavlovsk-Kamchatsky and Viluchinsk. The northern two-thirds of the peninsula is essentially uninhabited tundra and volcanic mountain country, much of it inside the Kronotsky State Biosphere Reserve. The southern third holds the population centres, the Russian Pacific Fleet bases, the regional airports, and the ports that connect the peninsula to the rest of Russia and to the international fishing economy of the North Pacific. Now place that peninsula in the larger geological architecture of the Pacific Rim. The peninsula sits directly above the Kuril-Kamchatka Trench, the subduction zone where the Pacific Plate dives beneath the Okhotsk microplate. The trench runs offshore, parallel to the coast of the peninsula, at a distance of roughly 150 to 200 kilometers from the shoreline. In total length, the trench runs approximately 10,000 kilometers from the northern tip of Hokkaido in northern Japan up through the Kuril Islands chain, along the eastern margin of Kamchatka and around the Komandorsky Islands toward the Aleutian Trench. It is one of the longest and one of the most seismically productive subduction zones on the planet. The mechanical situation underneath the peninsula is this. The Pacific Plate, the largest tectonic plate on Earth, is moving in a roughly west-northwest direction at approximately 7 to 9 centimeters per year, as measured at the Kuril-Kamchatka margin. That convergence rate is among the fastest of any subduction zone in the world. The comparison to Cascadia is the most useful way to feel what that number means. The Cascadia subduction zone on the western coast of North America, the same kind of subduction zone driven by the same Pacific Plate, on the opposite corner of that plate, is converging at about 2.5 to 3 centimeters per year. The Kuril-Kamchatka rate is roughly 3 times faster. That ratio has a direct mechanical consequence. The Kuril-Kamchatka Trench accumulates the same amount of elastic strain in approximately 1/3 the time it takes Cascadia to accumulate the equivalent strain. The locked patches on the Kuril-Kamchatka interface, the patches where the two plates are stuck together, friction is preventing slip and strain is building, fill up on a faster clock. The recurrence intervals for magnitude 8 and above earthquakes on individual named segments of the Kuril-Kamchatka system are typically in the range of 70 to 150 years. The equivalent recurrence intervals for the full Cascadia margin are typically in the range of 200 to 600 years. The Kuril-Kamchatka system produces the largest class of earthquakes more than twice as often as Cascadia does, and on individual segments potentially 4 to 8 times as often. What this means in practical terms is that the Kuril-Kamchatka system is not a place where moderate earthquake clusters are routine background noise. It is a place where the geological clock runs fast enough that elevated activity on a known loaded segment has earned formal institutional attention from the National Seismic Authority responsible for monitoring it. The recurrence intervals are short enough that the gap between large events is measured in human lifetimes rather than geological epochs. The convergence rate is fast enough that the strain budget refills quickly after each large rupture, and the history of the arc, which we will cover in detail, is long enough and well documented enough that the pattern of how segments load, rupture and reload their neighbours is understood in some detail. There is one more number worth anchoring before moving forward, because it connects the Kamchatka side of this story to the California side in a way that most viewers will not have considered. The Kuril-Kamchatka Trench and the Cascadia subduction zone are not just similar kinds of geological features on similar kinds of tectonic boundaries. They are both edges of the same plate. The Pacific plate is being subducted beneath the Okhotsk microplate at Kamchatka. The Juan de Fuca plate, itself a remnant fragment of the once larger Farallon plate, driven by the East Pacific rise, is being subducted beneath the North American plate at Cascadia. The connection between the two margins runs through the Pacific plate itself. The two opposite corners of that plate are not geologically independent. They are connected by 103 million square kilometers of rigid oceanic lithosphere that has been moving as a coherent unit for tens of millions of years. What that connection means mechanically, how stress propagates across it, at what speed, at what amplitude, and whether that amplitude is large enough to matter, is the question that the second half of this story is built around. The place to start building toward that question is the other corner of the plate, where the California cluster has been running on the same 48-hour clock as the cluster off Kamchatka. The Pacific plate is 103 million square kilometers in area. The total surface area of the planet Earth is approximately 510 million square kilometers. The Pacific plate by itself accounts for roughly 20% of the entire surface of the planet. It is larger than every continent on Earth combined. It is by a substantial margin the largest single piece of lithosphere on the surface of the Earth, and it is, on the timescale of months to years, a single rigid body. That word, rigid, is doing a significant amount of work in geophysics, and it does not mean what it might first appear to mean. The plate is not rigid in the sense that it cannot bend or flex. It does. The plate flexes by tens of meters across the regions where it is being subducted, as the leading edge curves downward into the mantle along the Kuril-Kamchatka Trench and the Aleutian Trench and the Mariana Trench. It flexes upward where it rides over hot mantle plumes, the one beneath Hawaii being the most familiar example, which has left a chain of seamounts and volcanic islands stretching northwest across the plate's surface as the plate moved over the plume. It contains internal fault systems along which it deforms slowly over millions of years. Rigid, in the geophysical sense, means something more specific, that on the timescale of months to years and at the scale of the plate as a whole, it transmits stress through itself as a coherent mechanical object, rather than absorbing or dissipating that stress internally before it can propagate across the plate. The analogy that makes this most concrete is a steel bar. Push on one end of a steel bar. The push propagates through the bar as elastic stress, travelling at the speed of sound in steel, approximately 5 to 6 kilometers per second. By the time you have completed the push, the entire bar has redistributed its internal stress to accommodate the new boundary condition at the end you pushed. The other end has already responded. The Pacific plate works in a directly analogous way, except that the bar is 103 million square kilometers in area, and the speed of sound in oceanic lithosphere is approximately 6 to 8 kilometers per second. A stress change at one corner of the plate, say a large earthquake on the southern Cascadia margin off the coast of northern California, propagates as elastic stress across the full width of the plate in roughly 20 to 30 minutes. By the time half an hour has passed, the Kuril-Kamchatka margin on the other side of the Pacific has already received the elastic signal of that event. The communication is, on the scale of weeks or months, essentially instantaneous. What flows through that communication channel is small. This is the part the literature is careful about, and it is the part that determines what the simultaneity of the two present clusters can and cannot mean. The stress amplitudes that propagate from a large earthquake at one margin to the opposite margin at distances of 7 to 8,000 kilometers are on the order of 1 to 10 kilopascals. To put that in geological context, the tectonic stresses that drive earthquakes themselves, the stresses that accumulate in a locked fault patch over decades of convergence and eventually cause it to rupture, are on the order of 1 to 10 megapascals. 1 megapascal equals 1,000 kilopascals. The stress amplitude arriving at the far margin from a large earthquake at the near margin is therefore 3 to 4 orders of magnitude smaller than the local tectonic stress already present at the receiving location. A surface wave travelling across the Pacific from a Kuril-Kamchatka magnitude 8 event arrives at the Cascadia margin carrying a stress amplitude that is, at most, 1/10,000th of the local tectonic stress at the receiving margin. That amplitude is small. It is, however, not zero, and the literature has been documenting for 30 years cases where small stress amplitudes from distant large earthquakes do produce detectable triggered seismicity at the receiving margin, provided the receiving margin is already loaded close to its own failure threshold. The mechanism is not that the distant earthquake provides the energy for the triggered event. It does not. The triggered event releases local accumulated strain that was already stored in the rock at the receiving location. The distant earthquake provides only the nudge, the final small increment of stress that pushes a fault patch already near failure over its threshold. We will walk through that literature in detail. The specific papers, the specific magnitudes, the specific distances, and most importantly the specific threshold below which the nudge is too small to produce a detectable effect. There is a second mechanical consideration worth naming here, because it bears on the question of whether the two clusters might be jointly responding to something that goes beyond the direct stress transfer mechanism. The Pacific plate as a whole, over decadal timescales, can in principle accumulate transient stress asymmetries between its two primary driving forces. If slab pull on the western subducting margins, Kamchatka, Japan, the Aleutians, Tonga, run slightly faster than ridge push at the East Pacific rise on the eastern margin can compensate for, the plate as a whole spends a brief period under net tension. If the asymmetry reverses, the plate spends a brief period under net compression. These transient global stress states are difficult to measure directly with the present generation of geodetic instruments. They have been inferred from satellite-based observations of plate kinematics over the past 20 years of high-precision GPS measurement at margin monitoring sites worldwide. The observation window is still short relative to the timescales over which these asymmetries might oscillate. The honest scientific position is that plate-wide transient stress states probably exist below the current detection threshold, and that the question of how those transients interact with the loading clocks at individual margin segments is an active area of research that has not yet produced definitive answers. That open question is part of what makes the pattern visible tonight worth taking seriously, and part of what makes any strong claim about what it means premature. What the historical record of this arc can tell us is where the present cluster sits in the longer sequence of events that has been building on this margin for centuries. That record is where the story goes next. The California side of this story has its own event log, and it has been running on the same clock as the Kamchatka sequence. The first significant event in the California cluster arrived at 10 hours and 53 minutes Universal Time on June 3, 2026. A magnitude 5.7 earthquake struck the seafloor off the coast of southern Oregon, approximately 30 kilometers west-southwest of Pistol River. The epicenter sits in the open ocean off the southernmost stretch of the Oregon coast, in the patch of water where the Gorda Plate, the small, internally deforming fragment of oceanic lithosphere that occupies the southernmost corner of the Cascadia subduction zone, meets the southern locked zone of the Cascadia megathrust. The United States Geological Survey logged the event within minutes. The Pacific Northwest Seismic Network, operated jointly by the University of Washington and the University of Oregon with instrumentation funded in part by the USGS, confirmed the location and mechanism. A few hours later, at approximately 14 hours Universal Time on the same date, a magnitude 5.1 struck the seafloor off Petrolia, California. a small community in Humboldt County that sits near the southernmost extent of the Cascadia subduction zone, where the megathrust transitions into the more complex fault geometry of the Mendocino Triple Junction. The Mendocino Triple Junction is the point where three tectonic plates meet at a single location offshore Northern California: the Pacific Plate to the west, the Gorda Plate to the north, and the North American Plate to the east. It is one of the more geometrically complex plate boundary intersections on the planet, and it is the southern terminus of the Cascadia subduction zone proper. Through the evening of June 3rd Pacific Time and into the morning of June 4th, independent observers monitoring the USGS real-time feed logged additional events in the same offshore zone, a magnitude 4.5 and a magnitude 4.6, both in the Petrolia and Gorda Ridge system, both consistent in location with the southern Cascadia locked zone and the adjacent Gorda Plate interior. The total tally on the California side, as of this recording, sits at approximately 7 earthquakes above magnitude 4 in a tight cluster off the southernmost corner of the Cascadia subduction zone. The most recent California side event is, at the time of this recording, only a few hours older than the most recent Kamchatka side event. Both clusters are, as of right now, active. What gives the California cluster its local mechanism? What explains why it is happening when it is happening, independent of anything on the other side of the Pacific, is a geophysical process called episodic tremor and slow slip. The Pacific Northwest Seismic Network tracks this process continuously through its tremor catalogue, and the numbers from the past 30 days are notable. Approximately 2,694 catalogue tremor events have been logged on the Cascadia interface in the past 30 days, with the spatial centroid of those events concentrated beneath the locked southern segment that runs from Northern California through the southern coast of Oregon. 2,694 events in 30 days is a heavy tremor month by the standards of the Cascadia system. Episodic tremor and slow slip is not an earthquake in the brittle failure sense. It does not involve the kind of sudden, high-speed rupture that generates the seismic waves a network of seismometers detects as a discrete event. It is a slow, sustained vibrational signal that comes from creep on the deeper portion of the megathrust interface, the portion below the locked patch, where the two plates are slipping past one another gradually over weeks to months rather than rupturing in seconds. The signal is detectable on sensitive broadband seismometers as a low-frequency tremor that can persist for days to weeks, migrating slowly along the interface as the slow slip front propagates. The geophysically critical fact about episodic tremor and slow slip is what it does to the stress state of the shallow locked patch above it. Every cycle of slow slip on the deeper interface transfers a small but measurable increment of additional Coulomb stress upward onto the locked patch. The deeper interface slips slowly. That slip redistributes stress. A portion of that redistributed stress loads the shallow locked zone. Tremor counts on the deeper interface are, in this sense, a slow-loading mechanism applied to the upper locked zone, a way of incrementally advancing the failure clock on the patch that, when it eventually ruptures, will generate the kind of ground motion and tsunami that makes a Cascadia rupture one of the most consequential natural hazards in North America. The pattern of what has followed elevated tremor months on the southern Cascadia margin in recent years is not a deterministic predictor. Elevated tremor does not guarantee that a brittle event will follow on any particular timeline, but the pattern is consistent with the established geophysical mechanism. A magnitude 4.8 on the southern margin in early May followed an elevated tremor cycle. The magnitude 5.7 and the magnitude 5.1 cluster on June 3rd followed the current elevated tremor cycle. The mechanism, tremor loads the locked patch, the loaded patch becomes more likely to fail in brittle rupture, is the local explanation for why the California cluster is happening when it is happening. It is complete on its own. It does not require anything happening on the other side of the Pacific to explain it. And that completeness, as will become clear, is exactly what makes the simultaneity of the two clusters the interesting question it is. On the 26th of January 1700, the Cascadia subduction zone ruptured along its full length. The rupture extended approximately 1,000 kilometers from northern California to southern British Columbia. The seafloor lurched westward by perhaps 10 to 20 meters along that entire distance in a matter of minutes. The ground shaking was severe enough to be recorded in the oral traditions of indigenous communities along the Pacific Northwest coast. The tsunami it generated crossed the Pacific Ocean and struck the coast of Japan with waves large enough to damage coastal villages and leave a record in Japanese historical documents. A record that, when analysed by seismologist Kenji Satake and colleagues in a paper published in Nature in 1996, allowed researchers to reconstruct the date, time, and approximate magnitude of the rupture from the other side of the ocean. The event that left that record occurred on the night of January 26, 1700, at approximately 9 in the evening local time. The magnitude has been estimated at approximately 9.0. That was 326 years and 4 months ago. The paleoseismic record of the Cascadia subduction zone, assembled over decades of work by researchers including Brian Atwater at the USGS, Chris Goldfinger at Oregon State University, and their colleagues, using turbidite sequences on the seafloor, buried soil layers exposed in coastal marshes, and drowned forest remnants preserved in tidal zones, extends back approximately 10,000 years and documents a series of full and partial margin ruptures. The recurrence intervals between full margin events vary considerably. Some intra-event intervals in the record are as short as approximately 200 years. Some are as long as approximately 1,000 years. The average across the full record is in the range of 500 to 600 years, but the most recent intra-event interval before 1700, the gap between the previous full margin rupture and the 1700 event, was approximately 300 years, and the interval before that was approximately 291 years. The paleoseismic record for the most recent 4,000 years, which is the period with the highest resolution documentation, shows no intra-event interval longer than approximately 500 years and a clustering of intervals in the 250 to 350 year range. The present intra-event interval, 326 years, is longer than any documented intra-event interval in the most recent 4,000 years of the Cascadia paleoseismic record. That sentence deserves to be read carefully. The current gap is not within the normal range of Cascadia recurrence. It is at the outer edge of what the 4,000-year record documents as possible. This does not mean the next rupture is overdue in any deterministic sense. Subduction zone ruptures do not operate on a fixed schedule. The elastic strain accumulation process is continuous, but the failure threshold is set by a complex combination of fault geometry, fluid pressure at the interface, temperature, and local material properties that vary across the locked zone. What it does mean is that the conditional probability of a full or partial margin rupture, given that 326 years have elapsed since the last one, is elevated relative to where that probability stood 100 years ago or 200 years ago. The Kamchatka cluster also has a complete local mechanism. The 2024 magnitude 8.8 earthquake ruptured a substantial portion of the southern Kuril-Kamchatka segment, but did not extend the full geometrically capable length of the loaded zone. The unbroken neighbour segment, the piece of fault between the northern terminus of the 2024 rupture and the next major structural barrier further north, inherited a Coulomb stress increment from the 2024 event and has been loading on top of that inherited increment ever since. The cluster developing on that segment right now is consistent with the natural mechanical evolution of a fault patch that has been stress advanced by a large neighbouring rupture and is continuing to load toward its own eventual failure threshold. So here is the centred framing, stated as plainly as possible. 2 clusters, each with a complete local mechanism, each on a segment that is at or near the outer boundary of its documented loading range, each still active as of this recording. The fact that both loading clocks have arrived at firing window states at approximately the same calendar moment is, on the most defensible reading, a coincidence. The kind of coincidence the global subduction zone catalogue produces a small number of times per year when independent segments on the same large plate happen to be simultaneously in elevated states. 2 stopwatches that started ticking at different times, happening to chime in the same hour because both were close to their next chime. That reading is correct at the level of local mechanisms. It is also, taken alone, not quite a complete answer to the question the pattern is asking. The question the audience-facing instinct keeps returning to is not whether each cluster has its own explanation. It is whether something about this particular calendar moment has made both clocks tick a little faster at the same time. To pursue that question honestly requires going first to the historical record of what this trench has done before. because the most important context for interpreting a moderate cluster on the Kuril-Kamchatka margin is not the catalogue from the past 36 hours. It is the catalogue from the past 300 years. And that record begins with an event in the pre-dawn hours of November 5th, 1952, that remains one of the largest earthquakes in the history of modern seismological measurement. In the pre-dawn hours of November 5th, 1952, an earthquake of magnitude 9.0 struck the seafloor off the southern coast of the Kamchatka Peninsula. It became known in the international seismological literature as the Severokurilsk earthquake, named for the small Soviet town on Paramashir Island, the northernmost of the Kuril Islands, that took the direct force of the rupture and the tsunami that followed within minutes of the shaking stopping. The event is the fifth largest earthquake ever recorded by modern seismographic instruments. It is exceeded in the instrumental record only by the 1960 Chile earthquake at magnitude 9.5, the 1964 Alaska earthquake at magnitude 9.2, the 2004 Sumatra-Andaman earthquake at magnitude 9.1 to 9.3, depending on the source model used, and the 2011 Tohoku earthquake at magnitude 9.1. The Severokurilsk earthquake sits in that very short list. 5 events in roughly 70 years of reliable instrumental recording, of the largest earthquakes humans have ever measured. It is not a historical curiosity. It is one of the defining events of the modern seismological catalogue. The rupture extended over approximately 600 kilometers of the southern Kuril-Kamchatka Trench, from the southern tip of the Kamchatka Peninsula down through the northernmost Kuril Islands. The rupture was a megathrust event on the interface between the subducting Pacific Plate and the overriding Okhotsk microplate, at depths spanning the same 10 to 45 kilometer range that the present cluster is now activating. The fault patch that ruptured had been accumulating elastic strain since the previous large event on that segment, a process that had been running, silently and invisibly, for decades before November 5th, 1952. When friction finally gave way, the seafloor lurched approximately 20 meters along the rupture surface in a matter of minutes. That 20-meter displacement of the seafloor is what generated the tsunami. The water column above the rupture was pushed upward by the sudden vertical motion of the seafloor. That upward push propagated outward from the source in all directions as a series of long wavelength waves, moving at speeds of approximately 700 to 800 kilometers per hour in the deep open ocean, roughly the cruising speed of a commercial jet aircraft. The waves are nearly invisible in the open ocean, where their height may be less than 1 meter, spread across a wavelength of several hundred kilometers. They become dangerous only when they reach shallow water near a coastline, where the slowing wave compresses and its height increases dramatically. The tsunami reached the southern Kuril Islands within 15 minutes of the earthquake. It reached the southern Kamchatka coast within 30 minutes. It crossed the open Pacific and arrived at Hawaii roughly 6 hours after the earthquake, with wave heights at Hilo Bay of approximately 12 feet. Enough to cause significant damage to harbour facilities and to alert the Pacific-wide tsunami warning network, which was at that time still in its infancy. It reached the western coast of South America in roughly 22 hours, with measurable wave heights recorded at tide gauges along the Chilean coast. It was the most extensively documented trans-Pacific tsunami of the 20th century, until the Sumatra-Andaman event of 2004 superseded it in both scale and global reach. The human consequences in Severokurilsk were catastrophic by any measure. The town sat at low elevation directly facing the ocean on Paramashir Island, less than 200 kilometers from the epicenter. The first waves arrived within 15 minutes of the shaking, before most residents had time to move to higher ground. Wave heights in Severokurilsk reached approximately 15 meters, roughly 50 feet, above normal sea level. The town was inundated completely. Structures that survived the ground shaking were swept away by the water. The official Soviet-era death toll was suppressed for decades as a matter of state policy. The Soviet government did not publicly acknowledge the disaster in any detail at the time it occurred. The figure that appears in the modern seismological literature, approximately 2,336 deaths, has been derived from post-Soviet archival research conducted after the dissolution of the USSR made those records accessible to researchers. That figure is the best available estimate. It is quite possibly an undercount. The actual number of people who died in Severokurilsk and the surrounding area on the morning of November the 5th, 1952, may have been higher, and the archival record is not complete enough to resolve the uncertainty with confidence. The 1952 event is the reference point against which every subsequent large earthquake on the Kuril-Kamchatka arc is measured, and it is the starting point for understanding the pattern of segmented rupture and stress redistribution that has governed this arc's seismic behavior for the past 70 years. It is also, crucially, a data point about what the arc is capable of producing, and what the segment hosting the present cluster sits adjacent to in the history of this system. The 1952 rupture did not happen in isolation. It happened as part of a long sequence of large events on this arc, each of which loaded the segments around it and contributed to the stress state that eventually produced the next large event somewhere along the system. Understanding that sequence, the domino pattern the literature has converged on for how long subduction zone arcs fail, is what places the present cluster in its correct historical frame. That pattern and the specific events that constitute it on the Kuril-Kamchatka arc from 1952 through 2024 is what the record shows next. The 1952 rupture did not end the story on the Kuril-Kamchatka arc. It began a sequence that the literature has spent decades reconstructing, and that sequence is the context without which the present cluster cannot be correctly interpreted. The pattern the literature has converged on, after analysis of this arc and others like it around the Pacific Rim, is sometimes called domino segmentation. The name is imperfect because it implies a speed and a determinism that the actual process does not have. Real dominoes fall in sequence over seconds. Subduction zone segments fail in sequence over decades. But the underlying logic is similar. A large rupture on one segment releases the elastic strain that had accumulated on that patch. The release redistributes Coulomb stress onto the segments immediately adjacent to the ruptured patch, the segments on either side that were being loaded by the same long-term convergence process, but had not yet reached their own failure thresholds. The redistributed stress does not cause those adjacent segments to fail immediately. What it does is advance their failure clocks. It adds an increment of stress on top of whatever local tectonic stress was already accumulating on those segments. The adjacent segments then continue loading from their own local tectonic process plus the inherited increment from the neighbouring rupture, until they reach their own failure thresholds, at which point they rupture in turn, redistribute stress onto their own neighbours, and the sequence propagates. The post-1952 sequence on the Kuril-Kamchatka arc follows this pattern with reasonable fidelity. The 1952 rupture covered the southern Kamchatka and northern Kuril segment. The segment immediately to the north, the central Kamchatka portion of the arc, hosted a magnitude 8.3 earthquake in 1959, 7 years after the 1952 event. 7 years is, in the context of subduction zone loading times, a short interval. The 1959 event is consistent with the interpretation that the central Kamchatka segment had already been loaded close to failure before 1952 and needed only the relatively modest Coulomb stress increment from the 1952 rupture to advance it to failure on a compressed timeline. The segments to the south of the 1952 rupture, the central and southern Kuril Islands portions of the arc, hosted a magnitude 7.5 event in 1963 and another magnitude 7.5 in 1969. Both events sit on the portions of the arc that the 1952 rupture loaded most directly on its southern flank. Both occurred within 17 years of the 1952 event. Both are consistent with the domino model, in which inherited Coulomb stress from a large neighbouring rupture accelerates the failure timeline of adjacent segments. The sequence continued through subsequent decades. The 1997 Kronotsky earthquake on the central Kamchatka portion of the arc reached magnitude 7.8. The 2006 Kuril earthquake reached magnitude 8.3. The 2007 Kuril earthquake on an adjacent segment reached magnitude 8.1, striking less than a year after the 2006 event, on a segment that had been loaded by the 2006 rupture's Coulomb stress redistribution and apparently needed less than 12 months to reach its own failure threshold as a result. The 2006 and 2007 pair is one of the cleaner examples in the modern instrumental record of rapid sequential failure on adjacent subduction zone segments driven by Coulomb stress transfer. The historical record extending before 1952 reinforces the pattern. The 1923 Kamchatka earthquake reached approximately magnitude 8.5 on a northerly portion of the arc. The 1841 Kamchatka earthquake was a comparably sized event further north. The 1737 Kamchatka earthquake, recorded in Russian colonial archives from the early period of Russian exploration of the peninsula, was another similar scale event. The historical record of large Kuril-Kamchatka events extends backward at least 3 centuries, with magnitude 8 and above events recurring on the various segments of the arc at intervals of 70 to 150 years for each individual segment. The arc as a whole has been producing the largest class of earthquakes continuously throughout the period of historical documentation. What the full sequence from 1737 through 2007 establishes is that the Kuril-Kamchatka arc is not a system where large earthquakes occur as isolated, independent events separated by long periods of quiescence. It is a system where large earthquakes occur in clusters and sequences, where each event loads the segments around it, and where the time between a large rupture on one segment and a large rupture on an adjacent segment ranges from months to decades depending on how loaded the adjacent segment already was before the stress was redistributed onto it. That framework is the lens through which the 2024 magnitude 8.8 must be read, and through which the present cluster, developing on the segment immediately adjacent to the 2024 rupture's northern terminus, on the piece of fault that the 2024 event left behind, must also be read. The 2024 earthquake is the most recent large event in this long sequence. The present cluster sits on the segment that the 2024 event most directly loaded. The institutional response to that loading, the advisory that has been in place since the months following the 2024 rupture, is the formal acknowledgement by the relevant National Seismic Authority that the loading is real, that it has been quantified, and that it warrants elevated public attention. That advisory, what it covers and what it means in operational terms, is what the record turns to next. In late July of 2024, an earthquake of approximately magnitude 8.8 struck the southern portion of the Kuril-Kamchatka Trench. It was the largest earthquake recorded anywhere in the world in 2024. By some independent measures, depending on which moment tensor solution is used and which depth model is applied to the source inversion, it was the largest earthquake recorded anywhere in the world since the 2011 Tohoku event in northern Japan. The energy released was approximately 10 to the 22nd joules. To make that number concrete, the magnitude 5.7 off Pistol River, Oregon, on June 3rd of this year released approximately 6 times 10 to the 13th joules. The 2024 magnitude 8.8 released roughly 100 million times more energy than that. The magnitude 5.2 off Kamchatka, on June 3rd of this year, released approximately 10 to the 13th joules. The 2024 event released roughly 10 million times more energy than that single event, and it released it in a matter of minutes along a rupture surface extending several hundred kilometers along the southern Kuril-Kamchatka arc. The rupture generated a trans-Pacific tsunami. The tsunami was recorded at tide gauges in Hawaii, in Alaska, and along the South American coast within hours of the earthquake. Ground shaking was felt across the entire Kamchatka Peninsula and into the northern Kuril Islands. The event triggered evacuations in coastal communities across the northern Pacific Rim and activated tsunami warning systems that had been designed and refined in the decades since the 1964 Alaska earthquake, and the 2004 Sumatra-Andaman event demonstrated how far and how fast Pacific tsunamis could travel. The detail that matters most for tonight is not what the 2024 rupture did. It is what the 2024 rupture did not do. The rupture did not extend the full geometrically capable length of the loaded segment. This is not unusual. The literature on megathrust rupture behavior, including the extensive body of work that followed the 2011 Tohoku earthquake, which itself failed to rupture the full extent of the northern Japan loaded zone, has converged on the framework that megathrust ruptures on long subduction zone arcs frequently terminate short of their geometrically capable maximum extent. They terminate at structural barriers, places where the geometry of the subducting slab changes abruptly, where the seismic coupling coefficient on the interface shifts from high to low, where the thermal structure of the interface transitions from the brittle failure regime to the ductile creep regime, or where the local hydrology of the fault zone changes the effective normal stress on the interface, enough to alter its frictional behavior. When a rupture terminates at such a barrier, it leaves a piece of fault on the other side of the barrier that was not part of the rupture, but that was being loaded by the same long-term tectonic process as the segment that did rupture. That leftover piece of fault, referred to in the literature as the unbroken neighbour segment, then finds itself in a specific and quantifiable stress state. It carries its own locally accumulated tectonic stress, whatever had built up on it in the years and decades before the neighbouring rupture. On top of that, it now carries an additional increment of Coulomb stress transferred onto it by the neighbouring rupture's slip distribution. The unbroken neighbour is, in the language the field uses, stress advanced. Its failure clock has been moved forward by an amount that can in principle be calculated from the slip distribution of the neighbouring rupture and the geometry of the receiving fault. The 2024 magnitude 8.8 ruptured a southern portion of the Kuril-Kamchatka segment. Post-event source studies, the detailed analyses of seismic waveforms, GPS displacement records, and tsunami waveform inversions that were published in the months following the event, mapped the slip distribution across the rupture surface. The slip distribution showed concentrated displacement in the central portion of the rupture, tapering to lower displacement at both the northern and southern ends. At the northern end of the rupture, the slip distribution tapered to essentially zero, somewhere short of the structural barrier that the pre-event geodetic and geometric analysis had identified as the likely northern terminus of the loaded segment. That gap, the portion of the geometrically loaded segment that was not part of the 2024 rupture, is the unbroken neighbour segment. It sits between the northern terminus of the 2024 rupture and the next major structural discontinuity further north on the Kamchatka portion of the arc. The present cluster is occurring within or immediately adjacent to the geographic zone of that unbroken neighbour segment. The events logged by the GFC Potsdam, the European Mediterranean Seismological Centre, the USGS, and the Russian Academy of Sciences Geophysical Service over the past 36 hours are occurring on or near the piece of fault that the 2024 earthquake left behind. That is not a coincidence of location. It is the expected mechanical consequence of the 2024 rupture's incomplete coverage of the loaded zone. The unbroken neighbour inherited stress from its neighbour's failure. It has been loading on top of that inherited stress for the past year, and it is now producing the kind of cluster, sustained rate, full interface depth activation, tight spatial footprint that a fault segment under elevated stress produces when it is being pushed toward its next state transition. What that next state transition is, and when it arrives, is the question the Japan Meteorological Agency has been formally watching for since the months following the 2024 event. The Coulomb stress redistribution from the 2024 rupture onto the unbroken neighbour segment has been quantified in several published analyses in the months following the event. The estimates of the stress increment on the unbroken neighbour range from approximately 1 to 10 bars, depending on the exact geometry of the 2024 slip distribution used in the calculation and the depth at which the Coulomb stress is evaluated on the receiving fault. 1 bar is equal to 100 kilopascals, approximately 1/10,000th of the typical tectonic stress that drives subduction zone interface failure. In absolute terms, 1 to 10 bars is a small number. In relative terms, for the specific question of whether it advances the failure clock on the receiving segment, it is not small at all. The foundational literature on Coulomb stress triggering, King, Stein, and Lin, published in the Bulletin of the Seismological Society of America in 1994, documented the mechanism in detail and established the observational basis for the claim that stress increments of this magnitude on loaded receiver segments measurably advance the timing of subsequent failures. The King, Stein, and Lin paper analyzed the stress changes produced by the 1992 Landers earthquake in California and showed that the locations of subsequent earthquakes in the region were strongly correlated with the zones of Coulomb stress increase produced by the Landers rupture. The paper established the framework that has governed stress transfer research for the 3 decades since. A stress increment of even 1 bar on a fault patch that is already loaded near failure is sufficient to measurably advance the timing of the next rupture on that patch. The unbroken neighbour segment of the 2024 Kuril-Kamchatka rupture is, by the estimates in the published literature, carrying a Coulomb stress increment of 1 to 10 bars on a fault patch that was already loaded by decades of tectonic convergence at 7 to 9 centimeters per year before the 2024 event added its increment on top. The Japan Meteorological Agency reached the same conclusion through its own internal analysis in the months following the 2024 event. The agency issued a megaquake advisory covering the southern Kuril-Kamchatka an adjacent northern Japan trench segment. The advisory was made public through the agency's official communication channels. It was accompanied by detailed public messaging about earthquake preparedness, tsunami evacuation route planning, and household emergency supply recommendations directed at residents of the Kuril Islands, the southern Kamchatka coast, and the northern Japanese prefectures of Hokkaido and Aomori. The advisory has not been lifted as of this recording. None of this is hidden. The Japan Meteorological Agency's megaquake advisory documentation is publicly available on the agency's website in both Japanese and English. The scientific basis for the advisory, the post-event source studies of the 2024 rupture, the Coulomb stress transfer calculations for the unbroken neighbour segment, the conditional probability estimates for large events on the stress advanced segment, is published in peer-reviewed journals accessible through standard scientific literature databases. The institutional posture of the relevant national seismic authority toward the segment hosting the present cluster is one of formally documented elevated watch, supported by quantified stress transfer analysis, expressed through active public preparedness communication, and maintained continuously for the past year without revision downward. The advisory is not a prediction. The Japan Meteorological Agency is explicit in its official documentation that the advisory does not constitute a forecast of any specific magnitude, location, or timing for a future event. It is a flag. It is the agency's formal statement that the loading state of the unbroken neighbour segment is at a level where the conditional probability of a large event is elevated above the long-term background rate by a calculable amount, and that residents and emergency management authorities in the affected region should treat that elevated probability as operationally relevant to their preparedness planning. Now consider what the present cluster represents in the context of that advisory. The Japan Meteorological Agency issued the advisory because the unbroken neighbour segment was stress advanced by the 2024 rupture and warranted elevated watch. The present cluster is producing 8 to 9 magnitude 4.5 and above earthquakes in 36 hours on that same stress advanced segment, with depth activation spanning the full interface range from 10 to 45 kilometers in a tight 50-kilometer spatial footprint with no Amori decay in the event rate. The cluster is doing exactly the kind of thing on exactly the segment that the advisory was designed to watch for. The same institutional dynamic applies on the Cascadia side. The United States National Seismic Hazard Map, published and maintained by the USGS, has for decades placed the conditional probability of a magnitude 9 and above full margin Cascadia rupture in the next 50 years at approximately 10%. The Oregon Office of Emergency Management has published conditional probability estimates for a magnitude 7.1 and above partial rupture on the southern Cascadia segment at approximately 37% over the same 50-year window. The southern Cascadia cluster is occurring on the segment these institutional documents have flagged. 2 clusters, 2 officially elevated watch postures from 2 different national seismic authorities on 2 different sides of the Pacific, both developing simultaneously. The institutional alignment is not the same as a prediction, but it is the context that separates this particular instance of simultaneous opposite corner catalogue activity from a simultaneous cluster on 2 random Pacific Rim segments that no one had been formally watching. The question of what that institutional alignment means for how the simultaneity should be weighted is one the 3 readings framework at the end of this story addresses directly. Before that framework can be built, there is a body of scientific literature that determines what the physics of the plate actually permits and what it rules out when 2 clusters fire on opposite corners at the same time. That literature begins with a summer afternoon in the California desert in 1992. On the 28th of June, 1992, a magnitude 7.3 earthquake struck the eastern Mojave Desert of Southern California at a location called Landers. The rupture was a right lateral strike-slip event on a complex network of previously mapped but largely overlooked fault segments, with surface rupture extending approximately 85 kilometers across the desert floor. By the standards of California seismicity, it was the largest earthquake to strike the continental United States in 40 years. By the standards of the global catalogue, it was a moderate event, significant in its source region, felt across the western United States but not in the same magnitude class as the events that dominate the global seismic energy budget. What made Landers scientifically important was not the earthquake itself, it was what happened in the hours and days after the rupture, at locations far from the source. Within minutes of the lander's main shock, seismographs across the western United States began registering small earthquakes in places that had been seismically quiet in the immediately preceding weeks. The Long Valley caldera in the eastern Sierra Nevada of California, approximately 300 kilometers northwest of Landers, produced a cluster of small earthquakes within hours of the main shock. The Geysers geothermal field in northern California, approximately 800 kilometers from Landers, produced a detectable increase in local seismicity within the first day. The Yellowstone caldera in northwestern Wyoming, more than 1,000 kilometers from Landers, produced an increase in microseismicity that was detectable on the regional seismic network. Similar small clusters appeared at locations distributed across the western United States in the hours and days following the Landers main shock, all at distances of hundreds to more than 1,000 kilometers from the source, all in places that had been quiet immediately before. This pattern, the appearance of small earthquakes at distant locations in temporal coincidence with the passage of surface waves from a large main shock, became the observational foundation for what the literature calls remote dynamic triggering. The phenomenon had been noted anecdotally before Landers, but Landers provided the clearest and most extensively documented case in the instrumental record to that point, and it was Landers that prompted the systematic scientific investigation that established remote dynamic triggering as a recognized physical process. The paper that opened that investigation in a rigorous way was published by David Hill and colleagues in Science in 1993. The Hill et al. Paper documented the post-Landers triggered clusters at multiple distant locations, demonstrated that the timing of the increased seismicity at each location coincided closely with the calculated arrival time of surface waves from the Landers main shock at that location, and proposed the physical mechanism. Surface waves from a large earthquake carry transient stress amplitudes that propagate across the surface of the Earth at speeds of approximately 3 to 4 kilometers per second, slower than the body waves that arrive first, but carrying more energy per unit area over a longer duration. When those surface waves arrive at a distant location, they impose a transient oscillatory stress on the local fault system at that location. If the local fault system is already loaded close to its own failure threshold, if the accumulated tectonic stress on the local fault is close to the level at which friction can no longer prevent slip, the transient stress amplitude added by the passing surface wave can be enough to push the fault over that threshold and cause a small earthquake. The key point in the Hill et al. Mechanism is the source of energy for the triggered event. The triggered earthquake does not draw its energy from the distant main shock. The surface wave amplitude is far too small to provide the energy for even a small earthquake at the receiver location. What the surface wave does is provide the final nudge, the last small increment of stress that a fault patch already near failure needs to cross its threshold. The energy released by the triggered event comes entirely from the local accumulated strain that had been stored in the rock at the receiver location, sometimes for decades, waiting for exactly this kind of final increment. The distant earthquake provides the trigger. The local tectonic loading provides the energy. That distinction is not semantic. It determines the magnitude of what remote dynamic triggering can and cannot produce, a point the energy budget section of this story will return to in detail. The Hill et al. Paper established the basic framework. What followed over the subsequent 3 decades was a progressive expansion of the documented distance range and source magnitude range over which remote dynamic triggering has been observed. Each large earthquake in the global catalogue after 1992 became an opportunity to test the hypothesis at greater distances and from larger sources. The 2004 Sumatra-Andaman earthquake at magnitude 9.1 provided the most extensive test of all, and the results of that test determined the threshold numbers that matter most for interpreting what is happening tonight. Those numbers, the specific magnitudes and distances at which the literature has established that remote dynamic triggering is and is not detectable, are what the record turns to next, because they are the numbers that determine precisely what the present clusters can and cannot mean in the context of the connection between the 2 opposite corners of the Pacific Plate. The 2004 Sumatra-Andaman earthquake at magnitude 9.1 to 9.3 was the largest earthquake recorded anywhere in the world since the 1960 Chile event. It ruptured approximately 1,200 kilometers of the Sunda megathrust off the western coast of Sumatra and generated the most destructive tsunami in recorded history, killing approximately 227,000 people across 14 countries. It was also, from the perspective of the remote dynamic triggering literature, the most powerful natural experiment in the history of the field. Aaron Velasco and colleagues published the systematic analysis of post-Sumatra Andaman-triggered seismicity in Nature Geoscience in 2008. The Velasco paper examined the global seismic catalogue in the hours and days following the December 26, 2004 main shock and documented increased seismicity rates at receiver locations distributed across the entire planet. Not across the Indian Ocean basin, not across the Asian region, across the entire planet. Triggered seismicity was detectable in California, in Alaska, in the Central Asian Plateau, in Mexico, in southern Africa, at high-latitude locations in both the northern and southern hemispheres. The Velasco paper established that triggered seismicity from a magnitude 9 class source event is a genuinely global phenomenon, detectable at any location on the planet where local fault systems are loaded sufficiently close to failure to respond to the transient stress amplitude of the passing surface waves. The paper also established that the triggering effect did not require any particular tectonic relationship between the source and the receiver. The triggered locations were not all on the same plate as the source. They were not all on the same type of plate boundary. The only requirements were a large enough source event and a sufficiently loaded receiving fault. Fred Politz and colleagues published a follow-up analysis in Nature in 2012, examining the global triggered seismicity response to the April 11, 2012 East Indian Ocean earthquake, a magnitude 8.6 intraplate strike-slip event on the Indo-Australian plate. The Politz paper documented that even at magnitude 8.6, well below the 9 class threshold of the Sumatra-Andaman event, the triggering effect was detectable at receiver locations distributed globally, again conditional on those receivers being loaded sufficiently close to failure. The Politz paper established that the magnitude threshold for globally detectable remote dynamic triggering was at least as low as 8.6 and suggested it might be lower still. Emily Brodsky and Stephanie Prejean published the paper that established the lower end of the magnitude threshold in the Journal of Geophysical Research in 2005. The Brodsky and Prejean paper took a different approach from the Velasco and Politz analyses. Rather than examining the global response to a single very large event, it examined the historical record at a single, particularly sensitive receiving location, the Long Valley caldera in eastern California, one of the locations that had shown triggered seismicity after the Landers earthquake, and analysed that location's response to a series of source events spanning a range of magnitudes and distances over the preceding decades. The Long Valley caldera is an ideal receiver for this kind of analysis because it is a geothermally active, hydrothermally pressurized system in which the local fault patches are maintained close to failure by the elevated fluid pressures in the hydrothermal system. It is among the most sensitive receiving locations on the planet for remote dynamic triggering. If remote dynamic triggering is detectable anywhere at a given source magnitude and distance, it should be detectable at Long Valley. The Brodsky and Prejean analysis found a clear threshold. Source events above approximately magnitude 7.5 consistently produced detectable triggered seismicity at Long Valley, regardless of the distance between the source and Long Valley, provided the surface wave amplitude at Long Valley exceeded a minimum stress threshold of approximately 1 to 3 kilopascals. Source events below magnitude 7.5 did not consistently produce detectable, triggered seismicity at Long Valley, even when the source was relatively close. The threshold is not perfectly sharp. Local conditions at the receiver, the source mechanism, and the orientation of the surface wave stress relative to the receiver fault geometry all introduce variability. But the convergence of the Brodsky and Prejean analysis on the magnitude 7.5 range as the lower bound for consistently detectable hemispheric distance triggering has been widely accepted in the field. That is the number that applies directly to tonight. Magnitude 7.5. That is the approximate lower bound below which the literature does not support remote dynamic triggering at hemispheric distances, even at the most sensitive receiver locations. The present clusters are producing events in the magnitude 5.1 to 5.7 range. They are below the magnitude 7.5 threshold by approximately 2 full magnitude units. On the logarithmic moment magnitude scale, 2 magnitude units correspond to a factor of 1000 in seismic moment, and a factor of approximately 32 in energy release. The present clusters are not, by the existing literature, large enough to be triggering each other across the Pacific through remote dynamic stress transfer. The surface wave amplitude at the Kamchatka receiver from a magnitude 5.7 source at 7,500 kilometers is by direct calculations several orders of magnitude below the 1 to 3 kilopascal stress threshold at which any documented case of remote triggering has been observed. The hypothesis that the two clusters are causally coupled through dynamic triggering at the magnitudes presently observed is not supported. That is the honest answer the literature gives. What would change that answer, the specific escalation on either side that would bring the triggering question back into live consideration, is a magnitude 7 or larger event on either cluster in the coming days. Below that threshold, the two clusters are not talking to each other through surface waves. What is happening in the solar wind above the planet at the same moment provides no alternative coupling pathway, and the arithmetic that establishes why is what the record addresses next. The same 48-hour window that contains the two earthquake clusters also contains a significant solar event. Active region 4455 on the visible solar disk produced an X 1.0 class solar flare at 11 hours and 19 minutes. Universal time on June 3rd, preceded by an M 9.3 flare and an M 7.7 flare from the same region in the prior 10 hours. Multiple coronal mass ejections from the June 3rd sequence are in transit through the inner solar system. The NOAA Space Weather Prediction Center in Boulder, Colorado has issued a G3 strong geomagnetic storm watch valid for June 4th through 5th, with a note in the official forecast discussion about the possibility of isolated periods of G4 severe geomagnetic storming during the peak of the multi-CME passage. The solar wind speed at the L1 monitoring position, the Lagrange point approximately 1.5 million kilometers sunward of Earth, where the Discover spacecraft maintains continuous solar wind measurement, is running at approximately 427 kilometers per second. The BZ component of the interplanetary magnetic field, which measures the north-south orientation of the solar wind's magnetic field and determines how effectively it couples energy into the Earth's magnetosphere, has already excursed southward to approximately -9 nanoteslas. The space weather event is real. It is happening at the same calendar moment as the two earthquake clusters, and a version of the claim circulates reliably in online conversations around weeks like this one, that the X-class flare, or the inbound coronal mass ejections or the geomagnetic storm, is somehow responsible for triggering the seismic activity. The claim takes several forms. Some versions invoke direct stress coupling between changes in the geomagnetic field and the stress state of rocks in the lithosphere. Some invoke a more diffuse energy transfer from the solar event to the solid Earth. Some invoke the High-Frequency Active Auroral Research Program facility in Gacona, Alaska, a research installation operated by the University of Alaska Fairbanks that uses high-frequency radio transmissions to study the ionosphere as a triggering mechanism. All of these claims, in their strong causal form, encounter the same problem. The problem is arithmetic, and the arithmetic is not subtle. An X 1.0 class solar flare releases approximately 10 to the 25th joules of total energy across all wavelengths and particle emissions combined. That number is genuinely difficult to feel at the scale of human experience, so a comparison is useful. The total annual energy consumption of the entire human civilization, every power plant, every vehicle, every heating system, every industrial process on Earth for a full year, is approximately 5 times 10 to the 20 joules per year. An X 1.0 flare releases in a few minutes approximately 10,000 years of total human civilizational energy consumption. The number is staggering. The X 1.0 is also, it is worth noting, the smallest of the X-class flares. Solar flare classification is logarithmic. An X10 flare releases 10 times more total energy. An X100 releases 1,000 times more. The X 1.0 that fired on June 3rd is a strong flare, but not an exceptional one for an active sun near solar maximum. Now consider how much of that 10 to the 25th joules reaches the Earth in any form that could mechanically couple to the lithosphere and influence brittle failure of rock at the depths where earthquake nucleation occurs. The flare itself radiates the vast majority of its energy as electromagnetic radiation in the X-ray and extreme ultraviolet bands. That radiation travels at the speed of light and reaches Earth in approximately 8 minutes. When it arrives, it is absorbed almost entirely in the upper atmosphere, primarily in the ionosphere at altitudes of approximately 60 to 300 kilometers, and in the thermosphere above that. The absorption ionizes atoms in the upper atmosphere and heats those atmospheric layers by hundreds to thousands of degrees Kelvin. The effect is real and consequential for radio communications, which depend on the ionosphere's reflective properties and which can experience significant disruption during X-class flare events. The effect on the solid Earth below the atmosphere is essentially zero. The X-ray and extreme ultraviolet radiation does not penetrate to the surface. It does not impose any measurable mechanical stress on rock at depths of even 1 kilometer below the surface, let alone the 10 to 45 kilometers where the Kamchatka cluster's earthquakes are nucleating. The coronal mass ejections are a physically distinct phenomenon from the flare radiation. A coronal mass ejection is a large magnetized plasma cloud, protons, electrons, and entrained magnetic field, ejected from the solar corona at speeds of several hundred to several thousand kilometers per second. The June 3rd sequence of coronal mass ejections by the modeling produced at the NOAA Space Weather Prediction Center and the NASA Goddard Space Flight Center's Community Coordinated Modeling Center includes multiple ejections with a total integrated kinetic energy of approximately 10 to the 24th to 10 to the 25th joules across the full sequence. Again, a very large number. Again, the question is how much of that energy reaches the solid Earth in a form that could influence rock mechanics at seismogenic depths. The answer involves two successive reductions. The first reduction occurs at the magnetosphere. The Earth's magnetic field deflects the majority of the incoming plasma around the planet. The fraction of the CME's kinetic energy that actually couples into the magnetosphere during a geomagnetic storm, rather than flowing around the magnetosphere and continuing sunward past the Earth, is a small fraction of the total CME energy. The kinetic energy of the plasma that does couple into the magnetosphere and drive the ring current and auroral processes during a major geomagnetic storm is approximately 10 to the 17th joules. The second reduction occurs between the magnetosphere and the solid Earth. The magnetospheric and ionospheric currents that flow during a geomagnetic storm induce secondary currents in the conducting materials of the Earth's surface and upper crust. These geomagnetically induced currents are the mechanism by which severe geomagnetic storms damage power grids, disrupt pipeline corrosion protection systems, and degrade submarine cable performance. The total mechanical and electromagnetic energy that reaches the solid Earth through this induction pathway during a major geomagnetic storm is estimated in the literature on geomagnetically induced currents at approximately 10 to the 10th to 10 to the 11th joules. That is the number that matters for the earthquake triggering question. 10 to the 10th to 10 to the 11th joules. That is the total energy delivered to the solid Earth from a major geomagnetic storm through the geomagnetically induced current pathway. The upper bound of any estimate the peer-reviewed literature treats as physically plausible. Now compare that number to the energy released by a single magnitude 5.7 earthquake. The seismic moment of a magnitude 5.7 event, calculated through the standard moment magnitude formula that relates seismic moment to the integrated slip area and displacement of the rupture surface, is approximately 6 times 10 to the 13th joules. That is the amount of elastic strain energy that had been stored in the rock at the source location and was released when the fault patch failed. 6 times 10 to the 13th joules from one magnitude 5.7 earthquake. Compare the two numbers directly. The total energy delivered to the Earth's crust by a major geomagnetic storm, approximately 10 to the 11th joules at the upper bound. The energy released by a single magnitude 5.7 earthquake, approximately 6 times 10 to the 13th joules. The ratio is approximately 1 to 600. The earthquake released 600 times more energy than the geomagnetic storm delivered to the crust. That is comparing the storm to a single, moderate earthquake. The Kamchatka cluster has produced multiple magnitude 4.5 and above events, in addition to the magnitude 5.2 and magnitude 5.1. The California cluster has produced multiple events including the magnitude 5.7. The total seismic energy release across both clusters combined is several orders of magnitude larger than the total energy the geomagnetic storm delivered to the solid Earth. The storm did not trigger the clusters. The arithmetic forecloses that claim without remainder. The HARP claim forecloses even more decisively. The High-Frequency Active Auroral Research Program facility in Gakona, Alaska, operates at a maximum radiated power of approximately 3.6 megawatts, 3.6 million watts of high-frequency electromagnetic energy transmitted into the ionosphere for research purposes. To accumulate the energy released by a single magnitude 5.7 earthquake, the HARP facility would need to operate at its maximum output continuously for approximately 550,000 years. To accumulate the energy released by the 2024 magnitude 8.8 Kuril-Kamchatka earthquake, it would need to operate continuously for approximately 112 billion years. The age of the universe is approximately 13.8 billion years. The facility would need to have been running since before the universe existed at its maximum output without interruption to accumulate the energy of a single magnitude 8.8 earthquake. The arithmetic is not ambiguous. There is also no known physical mechanism by which high-frequency radio transmission into the ionosphere could couple mechanically to rock at seismogenic depths of 10 to 45 kilometers. The literature contains no paper proposing such a mechanism. The basic physics does not provide one. The claim does not survive contact with either the energy budget or the mechanism question. There is one more piece of the solar seismic relationship worth naming precisely, because the full picture requires it. Marchetti and colleagues published an analysis in Scientific Reports in 2020 of the statistical relationship between solar activity and global seismicity over multi-decadal catalogue windows. The Marchetti analysis found a real, statistically detectable correlation between solar activity indices and global earthquake rates over long time periods. The correlation is small in amplitude. The authors are explicit in the paper that the effect, if causal, operates as a small temporal modulator of seismic activity that was already primed to occur, a slight shift in the day on which an already loaded earthquake fires, not a generator of earthquakes that would not otherwise occur. The Marchetti correlation, taken at face value, would not produce the dense, large amplitude clusters visible on the Kamchatka and California margins tonight. It would at most shift by a small number of days the timing of events that were already going to happen on their own tectonic loading timeline. The strong claim that the X 1.0 solar flare or the inbound coronal mass ejections caused the two earthquake clusters is not what Marchetti and colleagues claimed, and is not what the energy budget permits. The weak version, that solar activity may modulate the timing of already loaded seismic events by a small amount, is a real scientific finding with a real published basis, bounded carefully by its own authors, and orders of magnitude too small in amplitude to explain what the catalogue is showing tonight. That leaves the two clusters standing on their own tectonic foundations. The Kamchatka cluster, driven by the Coulomb stress increment from the 2024 magnitude 8.8, on a segment already loaded by decades of 7 to 9 centimetre per year convergence, on a piece of fault the Japan Meteorological Agency has been formally watching for a year. The Cascadia cluster, driven by 2,694 tremor events loading the southern locked zone in the past 30 days, on a segment 326 years past its last full margin rupture. At the southern corner of a subduction zone the USGS has been formally modelling as elevated hazard for decades. Each cluster explained completely by its own local mechanism. Each cluster independent of the other in terms of the physics the literature supports at the magnitudes presently observed. Each cluster also, on its own terms, more notable than routine catalogue background. What the evidence assembled across this story so far does not yet answer is the question the audience-facing instinct has been asking since the first paragraph: whether the two clusters tell us something together that they do not tell us apart. That question has three defensible answers. The literature supports one more strongly than the others, but all three deserve honest articulation, because the one the literature does not most strongly support is not fringe. It is the edge of what the discipline can currently measure. The three readings, ranked by epistemic confidence and the specific signal that would shift the weighting among them, are where this story ends. Three readings of the pattern, all three defensible within the literature, only one most strongly supported, all three worth stating precisely, because precision is what separates a useful framework from a false sense of certainty in either direction. The first reading is the routine coincidence reading. Under this reading, the two clusters represent independent local activity on two independently loaded segments. Each segment has its own complete local mechanism that fully accounts for why it is producing the activity it's producing at this moment in time. The southern Cascadia margin is producing a cluster because 326 years of elastic strain accumulation on a segment whose paleoseismic recurrence maximum sits around 291 years, combined with 2,694 catalogued tremor events loading the locked patch in the past 30 days, have brought the shallow locked zone close enough to failure that moderate brittle events are the expected expression of that loading state. The southern Kuril-Kamchatka margin is producing a cluster because the 2024 magnitude 8.8 redistributed 1 to 10 bars of Coulomb stress onto the unbroken neighbour segment. That neighbour has been loading on top of the inherited increment for the past year at 7 to 9 centimetres of convergence per year, and the natural mechanical evolution of that loading state is producing the kind of sustained moderate cluster the catalogue's now recording. Both mechanisms are complete. Neither requires the other to explain it. The fact that both loading clocks have arrived at firing window states at approximately the same calendar moment is, under this reading, a coincidence. The kind of coincidence the global subduction zone catalogue produces a small number of times per year when independent segments on the same large plate happen to be simultaneously near their failure thresholds. Historical catalogue analysis of Pacific Rim seismicity going back to the 1960s puts the rate of simultaneous opposite corner clusters of comparable magnitude and density at approximately 1 to 3 times per year. That is not vanishingly rare. It is not the modal pattern either. It sits in the range of unusual but not unprecedented, the kind of observation that is more striking than the average week without being statistically extraordinary. This reading is the centered reading. It is the reading the literature most strongly supports at the magnitudes presently observed. It is the reading this account lands on as the most defensible single interpretation of what tonight's catalogue is showing. It is also the reading that, taken alone, does not quite satisfy the question the audience-facing instinct keeps returning to. The second reading is the layered precursor reading. Under this reading, the two clusters represent independent local activity on two independently loaded segments. That part is identical to the first reading, but each cluster considered alone is a more credible precursor signal than the routine baseline catalogue activity would suggest. The layered precursor reading does not require any coupling between the two clusters. It does not invoke the Pacific Plate as a shared mechanical object in any way beyond what the first reading already establishes. What it adds is a higher weighting on the possibility that each cluster, on its own segment, is the early expression of a loading state that will eventually produce a larger event on that segment. The literature on foreshock sequences supports this weighting. The 2011 Tohoku earthquake was preceded by a magnitude 7.3 foreshock, approximately 51 hours before the magnitude 9.1 main shock. The 2014 Iquique earthquake in northern Chile was preceded by a sequence of elevated seismicity that began approximately 16 days before the magnitude 8.2 main shock and included several magnitude 6 class events in the week immediately before the rupture. Both cases involved segments that were already known to be loaded, the northern Japan trench in the Tohoku case, the northern Chile seismic gap in the Iquique case, and both involved clusters of moderate events that in retrospect were foreshock sequences to much larger ruptures. In both cases, the foreshock sequences were not deterministically predictive in real time. They were recognizable as foreshock sequences only after the main shock occurred. But they established that the pattern, a cluster of moderate events on a loaded segment, sustaining for days to weeks without a Mori decay, is consistent with the precursor behavior that precedes some large megathrust ruptures. The literature is careful not to overstate this. Most clusters of moderate events on loaded segments do not culminate in larger ruptures. The conditional probability that a cluster like the ones currently active on either side of the Pacific will eventually produce a magnitude 6 or larger event somewhere in its evolution is estimated by Gutenberg-Richter scaling, the empirical relationship formulated by Benno Gutenberg and Charles Richter in the 1940s, establishing that for every one earthquake of a given magnitude, a fault system produces approximately 10 earthquakes of 1 magnitude unit smaller, at somewhere in the range of 15 to 25% over the full lifetime of the cluster. The conditional probability of eventually producing a magnitude 7 is closer to 2 to 4%. These are not predictions. They are the calibrated statistical baselines the global subduction zone literature has converged on for what clusters of this size and density tend to produce when their full evolution is considered. What the layered precursor reading adds, in operational terms, is a higher vigilance posture toward each segment considered separately. It is consistent with what both the Japan Meteorological Agency and the United States Geological Survey are actually doing tonight, monitoring more closely than baseline, maintaining active preparedness communication, and watching for whether either cluster produces a larger event that would shift the probability distribution substantially, The watch window the literature supports for foreshock sequence interpretation is days to weeks. Over the next several days, the catalogue will accumulate information that bears directly on whether the layered precursor reading is the better description of what is happening on each segment. The third reading takes the question one step further, to the level of the plate itself, and it is the reading that requires the most careful handling, because it is simultaneously the most speculative and the most difficult to definitively rule out. The third reading is the plate scale transient reading. Under this reading, the Pacific plate as a whole is currently in a transient stress state that is simultaneously elevating the failure probability on both opposite margins, not through direct dynamic triggering of one cluster by the other, which the literature has already ruled out at the present magnitudes, but through a broader mechanical condition affecting the plate as a single object. The sources from which such a plate scale transient might arise are several. An asymmetry between slab pull on the western subducting margins and ridge push at the East Pacific rise on the eastern margin. If slab pull has been running slightly faster than ridge push can compensate for over the past several years, the plate as a whole would be under a modest net tension that could incrementally advance the failure clocks at both its locked corners simultaneously. A slow viscoelastic relaxation propagating through the plate following the 2024 magnitude 8.8. The lithosphere is not a perfectly elastic body, and large stress redistributions propagate through it at rates determined by the viscoelastic properties of the lower lithosphere and upper mantle, which are slower than elastic wave propagation speeds and operate over months to years rather than minutes. A decadal scale oscillation in the plate's overall kinematic state, of the kind that has been inferred but not directly measured from the satellite geodetic record at margin monitoring sites worldwide. Any of these sources, or some combination of them, could in principle produce a transient condition affecting the plate as a whole that manifests as elevated failure probability simultaneously at both its most loaded corners. The third reading in its strong causal form, the claim that such a plate scale transient is demonstrably operating and is demonstrably responsible for the simultaneity of the present clusters, is not supported by present literature. The stress transfer literature does not have the tools to detect plate scale transients at the amplitude that would be required to meaningfully advance the failure clocks at both margins simultaneously. The geodetic network does not have the resolution to measure such a transient directly. The energy budget arithmetic already established rules out the solar event as the source of any such transient. The strong causal form of the third reading is speculation beyond what the data supports. The third reading in its weak form is a different matter. The weak form states simply that something might be contributing to the simultaneity of catalogue visibility on this particular week that cannot yet be measured with the instruments presently deployed, and that the inability to measure it does not constitute proof that it does not exist. The weak form is a defensible scientific posture. The research community continues to investigate plate-scale stress transients. The question of whether they exist below present detection thresholds is genuinely open. The honest scientific position is that the answer is probably yes at some amplitude, and that the question of whether that amplitude is large enough to influence the timing of events at both margins simultaneously is not yet answerable with confidence. The third reading in its weak form is where this account places the boundary of what can honestly be said. The strong form is not endorsed. The weak form is named and respected as the articulation of what the audience-facing instinct is reaching for, the sense that the largest mechanical object on the surface of the planet is showing something at both its ends at once, and that the question of whether that double signal means something beyond two independent clocks is not a foolish question to ask. It is not a foolish question. It is a question the discipline continues to investigate. It is a question that may eventually have a cleaner answer as the geodetic network improves, and the catalogue of simultaneous multi-margin events grows long enough to permit the kind of statistical analysis that would distinguish plate-scale correlation from independent coincidence. That answer is not yet available. So here is where this story lands. The centered reading is the first reading. Routine coincidence. Two independent loading clocks, each cluster explained completely by its own local mechanism. Layered on top of that for each cluster considered separately is the second reading. The layered precursor posture that both national seismic authorities are actively maintaining. The elevated conditional probability that each cluster on its own segment is the early expression of a loading state that may yet produce a larger event. The third reading in its weak form sits at the edge of what is honest to say, acknowledged, respected, not dismissed, and not inflated into a claim the literature does not support. The single observation that would most decisively shift the weighting among these three readings is a magnitude 6 or larger event on either cluster in the coming days. A magnitude 6 on either side would shift the weighting substantially toward the second reading for that segment, toward the foreshock interpretation, toward elevated conditional probability of a larger rupture. A magnitude 7 would shift it more substantially still. A magnitude 7.5 would cross the Brodsky and Prejean threshold and bring the question of remote dynamic triggering at the opposite margin into live, literature-supported consideration for the first time in this episode. The absence of escalation in the coming days would shift the weighting back toward the first reading, not confirming safety, not disproving the precursor interpretation, but weakening it progressively with each passing day of tapering activity. The watch window is days to weeks. The catalogue will continue to record. The two clusters, both still active as of this recording, will declare themselves one way or another over a timescale that is short relative to the decades over which the loading that produced them has been accumulating. The Pacific Plate has not declared what it is going to do. The two corners are showing that they are loaded. What the catalogue is showing is unusual but not unprecedented. What it means in the deepest sense is a question no instrument on Earth can presently answer with confidence. The honest thing left to say is that the next several days are when the picture will begin to come into focus, and that the number to watch on either cluster is the magnitude of the next event above 5. If that number reaches 6, the framing changes. If it reaches 7, the framing changes substantially. If it reaches 7.5, the other corner of the plate becomes a live concern in a way the literature fully supports. Until then, the watch is what there is, and the watch is what we do.